Right. In our previous presentation, I think you remember, we were talking about the range and the domain, but we didn't really touch the range as such, but we took the domain. But before we proceed to the range, I want to emphasize the following things about the domain. This is especially when you are dealing with rational expressions. Rational expressions or rational functions, I'm talking about functions of this nature. R of x equals to P of x over Q of x. And the obvious, for this function to be defined, it should be that x of q of x, must be different of 0. Remember, we said those things like a being a number different from 0, 0. These things are not acceptable as values of a function. They're actually undefined entities. So, for it to be defined, we mustn't have any situation like this. Are we together, guys? Okay. So now, looking at the domain of a rational function, I will emphasize and say, whenever you're asked to give a domain of a rational function, you must always worry about the denominator. In other words, you must always worry about Q of x. How? Why? Because already I've said Q of x is not supposed to be equal to 0. So all those x's which are going to make Q of x equal to 0 must be thrown out of the domain. Out there. So what I'm going to do? To do that thing, to determine the domain, we will always set up an equation like Q of x equals to 0. Solve that equation. It might have one or two solutions. Then we know that those solutions for that equation are not supposed to be in the domain. So those solutions, we're going to call them zeros of Q of x. Those will be zeros. The solution to this equation are going to be called zeros of Q of x. But if I talk in terms of R of x, the solutions are going to be called the poles of R of x. Please understand me carefully here. I'm telling me correctly here. A 0 for Q is a 0 for Q. But when I look at P over Q of x, I'm talking about R. Then that 0 changes the name and say P, a pole of x. That terminology, you must know it, you must use it. When I use it, you must know exactly what I mean. Is that clear? Now, example. Now, this is an example of a rational function, and I want to determine the domain. Now, f of x, I call this function f of x, and the function is 2x over x minus 1 brackets x squared. Sorry, let me just say x. Sorry, let me complicate this thing too early. Let me just say x plus 3. Now, I want to determine the domain. Now, we're going to use this notation for the domain of f. Just write domain of f. Always, in this case, the domain of f is going to be numbers. In this case, real numbers, such that we're going to give a condition that those numbers must satisfy. Then we close. Now, how are we going to determine the condition? In this case, that's why we're going to grab Q of x and say Q of x equal to 0. What I mentioned is somewhere there. Sorry for that, it doesn't look nice, but I hope I'm just focusing what we did there, we mentioned there. Now, after that, what do we do? We take Q of x, which is in this case x minus 1, x plus 3 equals to 0. This thing on its own is revision metric, solving quadratic equations, isn't it? After factorizing, you get to something like this, you can solve it. Then you can say, therefore, x is equal to what? S equal to 1 or is equal to minus 3. Why am I saying all there? Because remember, if you've got a product of two numbers is equal to 0, either one of the numbers is 0 or both are 0, isn't it? So that's why I'm saying that one is 0 or that one is 0. But my brother, can you excuse me? Can you close the door for us, please? Okay, sounds better. Now, let's see. What's going to happen now, we'll go back to what we noted here as a domain, and then put this condition that for that function to be defined, there should be an x which is equal to 1 or equal to that. So we can write now here, such, this line here, when you write it like that, read that line as such that x is different from 1 and x is different from minus 3, then that is the domain of the function. Are we together? So it's important, I repeat, it's important when you're dealing with a rational function, you must manipulate the denominator and see where it becomes 0, then you can determine the domain. Are we together, guys? Okay. So now let's go to another type of expression or another type of a function which also we've got to have some kind of special attention to something so that you can see what we need to do there. Now we're still talking about the domain, but in this case now what I want to do, I want to look at it, a function square root of, in this case when I'm talking about this thing a function, I'm considering this principal square root where I would only take the positive values only, isn't it? So let me take a situation where I got 4 plus x. Now the most important thing here now is the radical sign, square root. Let's take it just as square root of x. What do we know about this thing to be defined? We know, what do we know? For this to be defined, what should be condition on f? Sorry? It must not be? It must not be negative. Okay. So that means that x must be greater or equal to 0, because 0 is not negative, isn't it? Okay. So x is greater or equal to 0. So now when you come to here to analyze the domain now, it's still going to be the set of real numbers, sorry, such that x something something. Then we close there. But how are we going to do that? We're going to part from here. This is very important. We're going to part from here. Let me just highlight that thing by putting it in a, going to part from there. That is very important. Why is it important? We're now going to come to this function and say whatever is the argument of the radical sign must be greater or equal to 0. So that's why I'm going to say now x, sorry, I don't want to write in color there, x plus 4 must be greater or equal to 0. So this is an inequality which you must solve. Basically the procedure and the principles are the same like we're solving an equation. Whatever you do on one side of the equation, you do on the other, isn't it? That's the first important rule. And in my language, or not in my language, in mathematics, nothing moves across a sign and change sign. There's nothing which moves. You must use the properties of numbers. What properties of numbers are going to have here? We want a condition on x, but x is accompanied by 4, and the x is actually added to 4. What we're going to use? We're going to use this property of numbers, which says a plus minus a is equal to 0. And this is the same thing as minus a plus a, isn't it? So we don't want a number here accompanying 4. It will be better to have 0 because x plus 0 will actually give us x, isn't it? So what are we going to do? We're going to use this principle by saying x plus 4 plus minus 4 is greater or equal to 0 plus minus 4. Even if you leave the bracket there, say 0 minus 4, it says the same thing. Even here, leave the bracket, say 4 minus 6. You know that is the combination of signs, isn't it? But I'm writing it very explicitly so that people don't, those who are slow, they don't get confused and they lost what is happening, isn't it? So this one is going to give us 0. So we've got here x plus 0. But 0 minus 4 is just minus 4, isn't it? Then x plus 0 is x greater or equal to minus 4. So we've solved our problem. Then we come here to the domain and say this x must have a condition that it is greater or equal to minus 4. Because when it's minus 4, it's going to give us 0. And the 0 is included in this condition here, isn't it? Okay. So the other things you must very, very careful when dealing with the range, the domain, especially with the rational functions. Functions which are not rational, like polynomials. Let's look at polynomials x, like something like a0 plus a1. Those are coefficients which I'm not really interested in what they equal. They could be 0 somewhere. Some of them could be non-zero. a2 x squared plus plus an x to the power n. Functions like that, the polynomials, they are normally described as very nice functions. Why? They will never present any kind of nonsense like 0 over 0 or an a over a, not even infinity over infinity altogether. Because they don't present such kind of problematic situations, then they are normally called nice functions. So the domain for this one, I will say the domain of P is actually all the real numbers altogether. That is very important. Right. Can you now move on? Can you move on? Okay. But if you've got questions, please don't feel free to stop me and ask. Altogether. Okay. Then the next thing we needed to discuss was the range. The range. In the simple language, I said the range was the set of values of the function. The function has got its domain there, where it's like picking its input, and then the range is the set of the output. If you want to talk in that kind of input-output system language, that's the thing. So now, if we are now given, I'll use one function which is simple to try to get a sense of what exactly the range is. Let me talk about a parabola. I'll take a simple parabola, x squared what a nice parabola. Y is equal to x squared. That is our f of x, isn't it? Okay. Now, the parabola is a kind of a polynomial, but in this case, because it's one term, is a monomial, isn't it? It's a monomial. So this is x. This is the real lines, which is actually giving us the x-axis, and this is another real line, which is giving us the y-axis. So what's the function going to do? We're going to pick x here. Let me now use color there. You're going to put x here. Did the color change? No. We're going to pick x here and come up there, and then y would be somewhere there, and the x is somewhere. Remember what I said the other day. I said if you are in the presence of a curve like this, function f of x, a point somewhere there. I'm just using a dot to highlight the point there. A point like that has got two coordinates. The one coordinate is x, the other coordinate is f of x, but f of x is actually the y coordinate, is it? And the x coordinate is there. So as I run along here, I'm on the domain. I will always pick an x, go to the curve. From the curve, I can be able to read my y, of my y. Go there, and then I'm going to be able to read my y. If I come this side also, there I'll read off my y. Come there, I read on both sides. What is happening to y? Increasing or decreasing? Increasing, is it? Yeah. Does it have a limit on top which is going to stop for someone? So all these values of what I'm talking about here, there are things which are in the range of our f of x, isn't it? So now if I want to write the set range of x, it will be the values y, which are actually real numbers, out here, such that, can you tell me which is the smallest value of the function then? 0, which is somewhere here, is it? And after that, all the values are greater than 0, isn't it? Then we can say such that x is greater or equal to 0. Oh, good. So you are paying attention to what I'm writing. That is very good. That is very good. Don't look down upon that. It's very important to look at what your lecturer is doing. Otherwise, you will follow the leader and get into a big hole. What is happening? Oh, that is y greater or equal to 0. Now, do you have a good sense of what is the range now? Is it? Okay. Let me ask a question. Y equals to minus 15. Is it in the range of f? So this is not in the range of f. That's why I indicate that. That is not in the range of f. So now all the functions we're going to look at, you must try to figure out what is the domain, what is the range. You are going to be asked to do that. Those things. All together. Okay. Now, talking about the domain, also, sometimes I have already looked at this example, like the one with the additional numbers. That thing of excluding some x's from the domain. We are actually restricting the domain to a certain region. All together. That's what we call that a domain is being restricted to a certain region of the real line or a certain part of the real line. That's what it's called. That's restricting a domain. Now, after this now, I would like to discuss with you what we call piecewise defined functions. Did you hear what I said? Piecewise defined function. First of all, if I'm looking at a function like f of x equals to x plus 1 over x, it's a function which is given by one single expression. Altogether. But sometimes the functions are not given in more than one expression. Then we talk of piecewise defined function. And each piece of that would be restricted to a certain part of the real line. Altogether. So let me talk about that and say piecewise defined functions. Sometimes I'll develop some kind of short notation now. I think from now onwards I'm just going to say FNT for function, isn't it? When I'm writing that. Is that right? Okay. FTN something. Right. Piecewise defined function. I'll give you an example of a piecewise defined function for people to understand what we really are talking about here. So let's take f of x equals to then let me say minus x from for all the x's less than minus 1. And then another part is saying x squared for all the x's greater or equal to minus 1 and the less or equal to 1. Sorry, let me say less. Write less, not less or equal. There. Write less, write 1. Less. Then let's say x for the x is greater or equals to 1. There's something which I don't like here. Okay, something which I don't like here. Let me say here plus 1. Because as I'm writing, I think about the thing I'm thinking, and I'm liking to look at the future. Then I see the future is chaotic. Then I've got to be corrective somehow. So let's give it like that. Altogether. So what's going to happen now? If we were supposed to draw the graph of this function, this is a piecewise defined function. If we're supposed to draw the graph of this function, I think we'll do something like this. Then this is our real line and our y also real line. Now as you see there, we've got a restriction of a domain to minus 1 to 1 for one expression, which is here. Minus 1 to 1. Then we've got greater or equal to 1. Then we've got something else. Now, if we remember this function, y is equal to minus x, is a function which runs this way. You agree? And then if you look at, remember this one is a function which runs on the same axis. It will look like that. Out there. And if you look at this, what's happening now? This one, it is something which comes parabola, isn't it? Everybody's got that good picture, eh? Now imagine that diagram is very beautiful and nicely drawn. That's what you can do with your imagination. Altogether, you are looking at a very nice diagram, isn't it? Okay. So now, but we don't want the graphs, the whole graphs as they are. Yes, my friend. Okay. This graph here, because it's plus 1, it must go up there. Isn't it? Good for pointing that. I was still at my x squared in mind, which is remembering, forgetting that I corrected that thing there. Is that alright? So the graph we're looking at is actually the one at the top, the parabola, isn't it? Okay. So now, if we're going to present this function, we need the piece of this y equals to minus x, isn't it? But it should go also only before what? 1, isn't it? And minus 1, sorry. And the minus 1 is not actually included, isn't it? Do you see that minus 1 is not in the domain? Okay. So what we're going to do now? We're going to draw the graph and say, let's suppose our 1 is here. Then this graph, if it was getting to 1, it will get a point there, isn't it? It will minus 1, minus 1, minus 1 is 1 to be there. Then it becomes a line which comes this way, but doesn't continue there because it's not allowed by the definition of function, isn't it? Okay. Then when you come to the parabola, according to that, the parabola will start at minus 1. Is 1 minus 1 squared 1 plus 1 is 2, isn't it? So they will put 2 there, a 1 there, So for the parabola at -1 will be 2. And this 2, this is actually the domain of that x squared plus 1, isn't it? Because -1 is included. Then we put it like this. Notice that there's a difference between how I put there and how I put there. The dot, solid dot, means that the value is included, and that is in the domain of the function. So the parabola will drop from there, come, and rise. When it gets to 1, is actually 1 is not in the domain of the parabola, isn't it? Then you put another open circle there, isn't it? Then when it comes to the other line, is actually in the 1 is in the domain. So at the same level there, I will have a solid dot. Guys, what I'm doing now is something which you are going to be expected to know and know how to do. There are two things there. Know and know how to do. All together. Then the graph will go like that. That's my beautiful y is equal to f of x piecewisely defined. All together. Then after that I can ask several questions. Write the domain of f as a set. What is the range of this function, and so on and so forth. All together. Okay. So we are there. So at the same time here, we've actually solved two problems. We've discussed the graphical representation of a function and the expression given in what? In piecewise defined function. All together. So I think I'm going to stop there. This presentation is a part of today's lecture, and then we proceed to the next part of the lecture. For now, thank you for listening.